Very good morning to all of you. In this video, we are going to see linear integrator circuits, Unit 4, analog multiplier and PLL. This is Divya, working as Assistant Professor in the Department of VCE, R.M.K. College of Engineering and Technology, Chennai. Let's get into the topic now. The topic what we are going to see now is phase locked loop. In short, we call it as PLL. What we are seeing now is the block diagram of the phase locked loop. Here we have four basic elements. Before seeing about the elements of PLL, first let me tell you what is meant by PLL. Phase locked loops are the circuits that are used to maintain the synchronization between two signals. One is the input signal, other one is the output signal from the oscillator. How can we maintain synchronization between these two signals? Means by using the element called phase detector. This block detects the phase difference between the two incoming signals. One is the input signal, other one is the output signal of the VCO. So this phase locked loop, as we can see in the block diagram, consists of four blocks. The first block is phase detector block. My second block is low pass filter block. Third block is error amplifier block. And the fourth block is VCO, which stands for voltage controlled oscillator. This VCO stands the most important block of this PLL. So this phase detector is going to compare the two incoming signals. One is the input signal with the frequency called Fs, and other one is the signal from VCO, that is the feedback signal with the frequency called F0. So these Fs and F0 will be compared in this phase detector, and an output signal is produced by this detector, which is a function of the difference between the phase angle of the two input signals. So output signal for phase detector will be the difference between the phase angles of the two input signals. So this output signal of this phase detector will be a DC voltage. This DC voltage may have some high frequency noise. So in order to remove that high frequency noise, it is fed into a low pass filter where the high frequency noise gets removed. And this low pass filter output where the high frequency noise is removed is fed to error amplifier, because this output is often called as error voltage. This error voltage will be very small. It cannot be able to operate the VCO. In order to amplify that, we are giving that to error signal. So output of this error signal is called as error voltage or control voltage, that is going to lead the VCO, voltage controlled oscillator. Here VC is the control voltage, V0 is the output voltage of VCO, F0 is the output frequency of VCO, Vs is the input voltage of the input signal, Fs is the frequency of the input signal. So now there is no control voltage, which means there is nothing fed back from the error amplifier to the VCO. Then the VCO is said to be in free running mode, which means it is not getting forced to move to some other frequency. It will work on its own frequency. That frequency is called as free running frequency. Otherwise, in simple, we call it as center frequency F0. When there is no incoming control voltage, my output frequency is constant, that is equal to F0. We call it as free running frequency or center frequency. When the control voltage is non-zero, which means there is some signal that is fed back from the error voltage to the VCO, which means we have a phase difference between the two incoming signals of the phase detector. So output will be a function of the phase difference, and the high frequency noise is removed, the signal is amplified, and we are feeding it to the VCO. Means then the VCO cannot produce a signal whose frequency is now equal to F0. It is going to produce a signal whose frequency is equal to F, that is equal to F is equal to its own free running frequency F0 plus some constant into Vc. Vc is the control voltage. So what is this kV? kV is the voltage to frequency transfer coefficient of the VCO. kV is the voltage to frequency transfer coefficient of the VCO. So thus, when we have no control voltage over here, output frequency of VCO is F0. When we have a control voltage over here, output frequency is F, that is equal to F0 plus kV into Vc. That's what we have to remember. So now, okay, we are having some control voltage over here. Our output frequency is F. It is not is equal to F naught now. It is equal to F. So what is the aim of this VCO means? The aim of this VCO is to reduce the difference in frequency between the two signals, which means your VCO tries to make its frequency F naught to be equal to the incoming frequency Fs. That is the aim of this PLL circuit. So we call this action as capturing. So we are trying to capture the incoming input frequency. So how long we will capture means how long it will take for us to catch the incoming frequency Fs, which means when Fs is getting input and we are getting F naught as VCO, now we are changing that to a new frequency called F. Now F is trying to be equal to Fs. We call this process as capturing. Once the output frequency of VCO F is equal to the incoming frequency Fs, then the circuit is said to be locked. In locked condition, so now we don't have any frequency difference between the two incoming signals. Then what is the output of this phase detector means? This phase detector produces a constant DC level that is required to shift the frequency of VCO to the F. If we don't have any control voltage, then VCO output will get back to the free running frequency called F naught. We should not allow it. We have to make the VCO output frequency to be equal to Fs. So in order to maintain that, we should give some constant DC level to the VCO as a control voltage. So that will be produced by the phase detector. So once this action is done, we are saying like the PLL is said to be locked state. Once it is getting locked, if the input frequency changes from Fs to some other new value, PLL is able to track that frequency change of the input signal. Once it is locked to Fs, your PLL can track the changes in the incoming frequency. So thus the PLL is going to work in three different states. First state is free running state, where the output frequency of detector is always equal to F naught. We don't have any control voltage in that case. Second state is capture state. In capture state, we are having a control voltage such that the difference between Fs and F naught is trying to be 0. That state is called as capture state. Third state is called as locked state. In locked state, always the output frequency of VCO is always equal to the incoming frequency Fs. Thus your PLL works on three different states. It is able to capture the incoming frequency and it is able to track the changes in the incoming frequency. Let us see the spectrum of your PLL. This is the center frequency, oscillator frequency F naught. Here you can see we are having a capture range Fc. That is the range of signals over which your PLL can acquire lock. This is called as capture range. Once the signal got captured, the PLL can maintain a lock for a wider range of frequencies. The bandwidth for lock is more than the bandwidth that we use for capture. Once your frequency is getting captured, the PLL is able to maintain lock beyond the capture range also. That is the speciality of this PLL. So now I hope you understood the working of PLL, block diagram and about the spectrum of PLL. Thank you all.